What's up, YouTube? My name's Digital Andrew, and welcome to another IoT and hardware hacking tutorial. In this video, we're going to be wrapping up our series on doing a firmware modification to the TP-Link router. If you didn't catch the first 3 videos in the series, I'll drop links to them down below, but just as a quick recap, in the first video, we took a look at how to do chip-off firmware extraction. So we desoldered the chip from the board, the one that actually contained the firmware for the device. We were able to extract that then. And then in the second video, I showed how I like to make a jig that's soldered on to the board so that we can easily take the flash chip in and out of the board and our flash programmer. And then in the third video, we took a look at making a basic firmware modification. We looked through all of the different settings and things we would need to take into account to repack up the firmware. But all we did is just add in a basic echo that just printed out Digital Andrew was here in the init script. So in today's video, we're going to take a look at making a more impactful firmware modification. And what we're actually going to do is install a very basic C2, so that's command and control client on the router. And we'll set up some really basic C2 infrastructure, a server that's going to allow us to send commands to the router and see the response. So I'll go over, the code for the C2 client and how we're going to pack that up and, get it onto the device. We'll take a look at all of that throughout this tutorial video. So with that being said, let's hop over to the computer now and take a look at how we're going to do this. Okay, so I'm back in that directory we've been using for the router. And you'll recall we have, our patch root file system here, which is the one we're going to patch, and our utils here, which has our script for packing the firmware. So what I've gone and done ahead is I've created a C2 folder here, which has all of the infrastructure for our C2 client and server. And I've written a basic C program here that just uses raw sockets to be able to connect back to our server. So the reason for that is, again, we're on an embedded device and we don't really have access to commands like curl or wget. And we want to make this have the least amount of dependencies that it does, so it increases our chances of it actually working. So in these videos, I don't like specifically just like reading out every single bit of code because I don't think that's helpful for you. So what I am going to do is I'm going to go through and show, the gist of what's going on here, but I will put all of this code up in the GitHub repo for this router. So if you want to go and take a look through it more in depth, I've tried to add as many comments as I can as well. So you can clone that repo and then you can also run this against the router if you want as well. So let's take a quick look through the client here. So again, we're including all these libraries here, and then you'll need to change this to, wherever you're going to run your command and control server. So for me, I'm doing this all locally, but there's no reason. I mean, most routers you can connect back out to the internet as well. So there's really no reason why you couldn't do this somewhere in the cloud as well. I'm just going to be doing it all locally. So we got a bunch of functions that we define here at the start. So we've got one for executing a command. So this is what's actually going to allow this client then to run a command, because essentially what it's going to do is pull out to the server, see if there's a new command. If there is, it's going to try and run that command and then return the result of that back to the server. So you'll notice here, we're doing that with popen, which opens a new pipe and then runs the given command here. So we're going to pass this command into the function, which you'll see we'll get later from the server. And then we read the output, and then we actually return that as the result. So we return the output that we get. Here is where we create a socket connection. So this is what allows us to have that raw socket to connect to the server. So, I mean, the standard way of doing this, sock equals socket, AFI net, sock stream. We set the timeout here, and then this is where we're configuring the server address, which we're pulling from above, the port and IP address for it. And then we actually just connect to the server here using that socket. So we're going to use this as a function here to connect to the server. We'll use that later. We've also got a function here to make our HTTP GET requests, because we're going to need those to get the command that we're supposed to be running. So here's where we build the request here. And here's where we send the request, receive a response, and then close our sock. And then we should be getting JSON returned back to us. That's how the server works. So here's where we get that JSON, and we actually parse it out, and then we return our response. We also have the ability to make a post request, because that's how we actually send back our response to the server. So again, similar to the GET request, but instead we're building a post here. Send the request, send that request, and then, close it and return that it was successful. If we got to here, it's successful. So we have a function here that just pulls the server for the command. So it's going to pull at a set time, and it's going to, you can see here, we're doing HTTP GET, and we're doing a GET for command is the endpoint. That's where that command lives. And this is where we actually then parse out what that command should be and return that. So essentially, this is just going to return back a command. And here's where we actually then submit the response to the server. So this is where we actually use the post here to send our post message back out. So that's how we are sending the post there. And then we've got our main here. So you can see some print messages, flush standard out. We got a infinite while loop here where we're just polling here. So we poll for our command. If we get a command, we do some checking to see if it's a new command, and then we just execute that command. And after we execute the command, we update our last command so that we can keep track of what the commands are that have been run. And we actually send the response to, which is right here, submit the response. So the reason we're keeping track of the last command is so that, the client handles, if you keep getting the same command is there, so it hasn't changed, it doesn't just keep running the same one over and over and over again. So again, pretty simple client here. And again, I'll put this in GitHub to give you an idea of how it runs. And then we can take a quick look at the server here. So again, running a really basic Flask server. And I just, copied some raw HTML right in here. We'll see how it looks. It's, it's super bare bones, just to give an idea of how this works. And then we've just got a couple routes. So of course we got our main web interface. We've got that route for updating the command. So this is actually for the web interface to update the API, so that in the web interface, we can change the command and then it will update in our API. We've actually got the one that just holds the command. So this is what the client is polling for. And then we have a route here where the device can send the response to us. And yeah, so fairly basic. And then we just open up our Flask server here, start up, open it up, and some printing. So again, very basic server. I'll add the code to this to the GitHub. So the next thing we should look at is the make file, because this is where we're actually going to compile this binary. And there are a few, things to pay attention to with that and some caveats. So of course, we are compiling this for an embedded Linux system that's running on MIPS little endian. So we cannot compile this natively for whatever architecture our host computer is running on. It's not going to work. So the first thing is we'll need to pick a compiler to use for our cross compilation tool chain. So I'm going to be cross compiling, which means I'm on an x86 computer right now, and then we'll cross compiler for MIPSL. Sometimes this can introduce issues. Usually it's okay for smaller things like this, but the other option is to try and find an architecture like where your target is and then compile on that. But I'm going to be cross compiling here. And again, I'm going to be using the MIPSL Linux GNU GCC for that. Now, this one usually works. I usually try, just standard GCC for like MIPSL or ARM or whatever for cross compilation. But, it is possible that they're using like a separate compiler or something like that. And you're going to have to play around a little bit more cross compilation can always be, something that's a little bit tricky to get the tool chain and everything right. But yeah, I found this one to work, and this is where I usually start, is with the, Linux, GNU, GCC, and then for whatever architecture you need. So then we do have a bunch of compiler flags here, though, and some of these are actually pretty important. So I just like to pull in warnings, all of the warnings, because usually, in my opinion, if you get warnings in C compilation, there usually is an issue. So I like to at least see those and look at it. But then these are the really important ones here. So this one is telling it to use the C99 standard. And this is really good for portability and cross compatibility. So if you really just want to make sure you're getting your cross compilation to work and it's going to work over there, this really helps that. Then this is actually optimizing for size. So we're trading out on speed and things like that to try and make this as small as possible, because again, we are working in an embedded environment, and then we are going to statically compile this. So that means that all the libraries and dependencies and everything are going to all be statically linked and inside of the binary. So this is what is going to make it a little bit bigger, but it's also going to make sure that we don't need to worry about what's on the device for libraries and things like that. It's all going to be included in the binary, which is what's going to make it more portable, to not have to worry about going and checking and seeing, what libraries, what version of the libraries they have, are they compatible with our code. So that's really the big, things that I've done here. Everything else here is just making this easier so that I can run make and build it. And then I also have a copy one here that allows me to copy this over to where we're serving the client. So let's run a clean here so we can clean this up now that we've taken a look at how this all works. So we're gonna make clean here. Perfect, we cleaned it. So now we can just go make, and we'll just go make all here. Perfect. And now we've got our IoT client. And then I'm gonna run copy here. Oops. Make copy. Oops. We got to run this one with sudo because it's in my serve file. So, okay. So let's quickly talk about what I'm doing here and why I'm doing this. So to actually test that this works now, before we try and do any firmware modifications on this device, we have TFTP, that's Trivial File Transfer Protocol. So what I'm going to do now is I'm going to use the UART connection to get into the device, and we're going to bring the client over with TFTP and make sure it works, because a lot of times when you're doing this compilation, and I've already refined this, off camera, but it takes, you got to keep working at it to see, are you have any dependencies, compilation options right? So it's a lot easier if you have TFTP, to just, bring it over that way, see if it runs, try and fix it, because then you don't have to keep reflashing the firmware. So that's why I copied it. I have TFTP set up on my computer here, and I have, there's just one directory that it serves out of. So that's why I copied it to that directory here. This is where it's served out of on my computer. So let's go ahead and connect with screen here. 115.2.0.0. So I'm going to power on the router right now. Okay, I'll just let these build logs come through here. So while those are coming in and it's reading the flash and everything, there's one other thing I want to take a look at here, which is I have a bash script here, which is this start_IoT_client.sh. So the reason for this is because, after we TFTP this and check it out, we're gonna take a look at the size, and it's going to be too big to actually put into the firmware, because this is something you're going to see with, IoT and embedded systems, is we're really limited on size. So on this one, we don't have enough actual space to put in another binary of that size. So what we can do, though, for our firmware modification is make sure that our C2 is always listening to be able to serve up the client itself. And then when it starts up the device, it's going to actually run this script. We'll run this start IoT client. And essentially what it's going to do is it's going to use TFTP here, really basic script, to download the client, make it executable, and then run it. And then, so every time we'll put this, to call this in that init script, instead of echoing our name out, we'll call this script, and then it's just going to download it. So that is what will give us our persistence. And I also want to demonstrate this because this is one way that potentially attackers can gain persistence if they aren't able to modify the firmware. So if they have an exploit that is WAN faceable, and they want to put like a client for like Mirai or something to make it part of a botnet, and they have no way to write to the firmware for persistence, what they can do is they can have their exploit, like, if they lose connection to the device because it power cycles and then it resets and they lose anything they've written to a temp folder, they can have their command and control server then go like, oh, I haven't had connection for like however long. I'm going to try and, send out, you reuse the exploit, send out to get the device to then download the client and then go from there. So that's how they can have persistence if there's a working exploit to get command injection without actually being able to modify that read-only firmware that's on the device. So again, one of the reasons I want to show this. So we've got our screen here. Should be able to clear this out here. Okay, clearing screen. Okay, so we've got our screen connection here, and we can actually just run this. So it's going to be here. I'll just copy this to make my life a little bit easier. Copy. And we need the client's path, which is going to be /temp/srv. Actually, we need /var/temp. And it's going to be IoT _ client. And then we need our IP address, which actually I'm going to need to connect to the Wi-Fi of this device here. I am connected. Perfect. So my IP then for this is 192.168.0.101. Okay, perfect. It's working. So now if we go into var and then temp, perfect, we've got that. So we'll just run chmod here. And then now I'm going to come in here, and I've got a venv here. I just like running all my Python stuff in virtual environments. So let's launch up this server. So we have Python 3 server.py. Perfect. It is running. So let us open that up actually here. So here is our very, very basic remote control. Again, nothing fancy here. So I'm just going to write pwd update command here. And then we've got our current command pwd. So that's just sitting there. And now if we just head over to here and we run /IoT client, you can see it received pwd submitting response to server. So it's just chilling, now sending that back. So if we head back over here to our server, we can see perfect. So now we've got the response here. So of course we could do, more malicious commands, or, we could list out the content here. So we go ls update command and run, ls, or we could cat out the shadow file, or really whatever we want. So you can see here, we're getting all of the, different directories and things that are inside of this. So now we have full remote control over this device. So the next step now is going to be to do this last firmware modification to make that persistent. So let's take a look at that now. Okay, so now that we've confirmed our compilation works, we brought the binary manually over to the router with TFTP and make sure that it actually ran and everything worked. Now, the last step for us to do is to actually automate all of this and add this in to the modified firmware so that when the router starts up, it automatically just does this all behind the scenes, so that, every time this router restarts, we have persistence that it's going to reach back out to our C2 infrastructure. So we're actually going to do a similar process again with our firmware modification to what we did with the manual one, where we're actually going to bring over the binary, that's the client, with TFTP, and then we're going to start that up. So the reason for this is there's just not enough space in, what we consider the read-only memory, where the firmware is actually stored. So in the boot process, though, this is actually going to get copied into RAM, and then there's going to be more space in the RAM where we have some writable directories like /var, for example, because the device needs to have some space where, it can write. And these are all temp directories that are all just existing in RAM. And what that means, though, is once we restart the device, all that's going to be gone again. They get inflated every time, or built up from the init scripts in the device. So what we need to do is modify those init scripts. So it's going to bring over our binary, our modified, or our C2 binary, and call it every time. So when the device restarts. So let's hop over to the computer now and take a look at how to do that. Okay, so you may recall from the previous videos that I set up this patch_RFS directory here. This is our root file system that our pack script is going to then, patch up as the new root file system. So any changes we want to make to our modified firmware, we'll make here. So we're going to go in here, and then inside of etc and init.d is the RCS script. So this is the script that gets called by the BusyBox init process. And you remember we made this modification before right here. Yeah, we added this. So what we're going to do is we're going to come down here and right at the bottom. So we're going to want to wait until after, networking is set up and all the, kernel modules and everything are loaded. And then I'm going to call our script. So we're going to go / and I'm going to use direct paths here just to make sure we hit this. So it'll be init.d, and then it's going to be start _IoT _client.sh. And then we'll need to make sure we actually bring this script over. So we've got enough room for this script. So copy this, come here, paste it in here just to make sure, come back to RCS. And then, so this will be fine at this point, but what I'm going to do just to make our lives easier is we'll add in some echoes here. There we go, echo. And then sometimes I'll do this if I'm like troubleshooting, is I'll just add like a bunch of equals here, like so. And then I'll just, add in a bunch of these, because when you're scrolling through really verbose logs, sometimes it's a pain to just need this. So we'll put this here. And then, yeah, maybe we'll add like an echo here that says like calling start _IoT _client.sh. Perfect. And we could put this here so we know when we're done too. So if we copy this here, put this here. Perfect. So now if we go, actually, let's just grab a new terminal so we can leave those there. Okay, and now we'll go into utils here, and then let's run our pack firmware. Perfect, that's all packed up. So now I'm gonna go power off the router, move the flash chip over to my XGECU, and we'll write this modified firmware over. Okay, firmware is moved over, so let's run the same commands that we did previously. Again, then we already got this identifier and everything off the chip in the last video. So we'll let this run. I'm gonna let mine write and run through. It's gonna take about a minute here to erase, read, and write and verify it again. Okay, our verification is done. So it's actually, before we plug this in, let's start up our server here. Perfect. And then in here, let's start up a screen so that we have this sitting and ready. Perfect. Okay, so now I'm going to move this chip back over to my router, power it up, and hopefully this will all work, and we'll get our C2 client working, connecting back to the server we just started. Okay, perfect. So just really quickly, I saw there flashing through to start up that script. So it's going to pause 2 minutes because remember, we need to let the networking and everything come back online for the router before it's going to be able to copy with TFTP. So let's give it a couple minutes here and we'll see if it comes online properly here. Let's launch up the server here. We'll open this up here. Let's give a command here. So we'll update this to ls. Perfect. And then give it about a minute here for the client to start up. Perfect. Okay, so we can see the commands start coming through. So ls worked. We got our response here. So if we actually hop back over now, you can see the client is just running. And again, we made it really verbose so that we see in the logs here. But yeah, now our firmware modification has taken place and we have full persistent control over this router. Hopefully you enjoyed this video and this series on the firmware modification for this TP-Link router. If you did and you made it this far, then please check and make sure you are subscribed, because I'm going to be putting out a lot more tutorial style videos on IoT and hardware hacking just like this one. And also, if you are interested in a more structured course like this, then make sure to check out the free course called All About UART that Matt Brown and I put out on his training platform. I'll drop a link to that down below here. It is 100% free, no credit card required. So if you're interested in this stuff, I would highly recommend checking that out. And again, thanks for watching this video.